Many times throughout the course, we've used the terms generic versus concrete to differentiate between types. When we say generic, we mean general or non-specific. When we use concrete, we mean actual or realized. We've seen generic types plenty of times before. As a reminder, a generic is a non-specific placeholder type or a stand-in for some future type. A generic adds flexibility by not hard-coding an exact type so that later code can use a variety of types in the place of the generic. The generic is the placeholder that allows us to write flexible code, and then later on, we substitute the concrete actual type. Just like with generic types, there are generic lifetimes and concrete lifetimes. A concrete lifetime is the actual region of code that a value exists in the program, which corresponds to the time that it exists at a single memory address. We saw from the examples in previous lessons that Rust understands the concrete lifetime of a value when it lives within a single function. Now, generic lifetimes are more abstract. A generic lifetime is a hypothetical lifetime, a non-specific lifetime, a future lifetime that has the potential to vary. We can declare these generic lifetimes in our code, and that will enable functions that similarly benefit from increased flexibility. These functions become more flexible because they can deal with various differing lifetimes. So in order to declare generic lifetimes, we use something called lifetime annotations. A lifetime annotation is a name or a label that we give to a lifetime, and it doesn't affect the code in any way. It doesn't change how long references live. It doesn't affect the logic in any way. It's exactly how a function parameter doesn't change the logic in any way or alter the implementation in any way. It's just a contract that we provide that the compiler will validate. So a lifetime annotation is a piece of metadata that we provide to the borrow checker that it enforces, that it validates. And it looks at what we do in the body of the function, and it says, yes, you are living up to what you promised to do. You are living up to the lifetimes that you provided and the relationships that you are declaring between your references, particularly the relationships between the parameters and the return values. So now let's transition to VS Code and take a look at this syntax in action. So let's talk about how we declare these generic lifetime annotations. This is really the heart of this section's content. What we're going to do is provide lifetimes for the select first two elements function from the previous lesson. We declare lifetimes inside angle brackets after the function name, just like we do with generic types. So after the function name, before the parameter list, I'll provide angle brackets. And then for each lifetime, we're going to begin with the apostrophe symbol. And that is what the compiler recognizes as a lifetime annotation. This symbol is often called a tick in the community. And the tick is followed by the lifetime's name, which serves as an identifier. And usually it's a single lowercase letter. So what you're most often going to see is something like this, a tick followed by a letter. So this is called tick A, and it is the presence of that apostrophe that allows the compiler to distinguish between a lifetime versus a generic. A generic would look something like this. It's just a letter or a word, right? As soon as we add that tick, that is how Rust understands it's a lifetime annotation, and then we actually need to give it a name. And A is just common because A is the first letter of the alphabet. Just like with generic types and their names, this lifetime name of tick A is arbitrary. It's up to the developer. We can call it tick Z or tick zoo, right? But the general convention is being short and then logically sequential. So if you have a single lifetime annotation, tick A is common. If you have multiple, then you follow it up with tick B, etc. It's also important to note that tick A is the full lifetime name. So we cannot use just the letter A by itself or whatever we write here. we need to include that apostrophe anytime we're going to be using this lifetime. So what tick A represents is some generic lifetime, some hypothetical lifetime, a future lifetime that we do not know yet in advance, or that has the potential to vary. A generic lifetime annotation like tick A doesn't add any value by itself. Just like if we declare a generic type T, but we don't use it for any parameter or return value, it's the same idea. The important thing is we have this lifetime annotation, and now we're able to use it to define the relationships between parameters and return values. So you can think of this lifetime as a marker, and that marker we can use to draw the relationships and the connections between lifetimes of parameters and return values. So tick A is like a stamp or a symbol that we can use. So what we're going to do is we're going to add the exact same tick A symbol after our reference operator in both our parameter of items and our return value. So right here, tick A, and then a space, and then right here, tick A, and then a space. So pretty confusing syntax. Once again, this is one of the most challenging topics in Rust. But what are we declaring here? The key takeaway here is that we are using tick A as a marker to indicate that the item's parameter's lifetime is related to the return value lifetimes. So you can think of this as a marker that allows us to draw an arrow from here to make this association, this connection. Let's be even more specific here. By specifying tick A as the lifetime, we are declaring that the returned reference right here, this slice, cannot outlive the referent for which items is a reference, which thus prevents dangling references. We are saying for some generic hypothetical lifetime called tick A, the returned reference must live within the lifetime of the referent that items is a reference to, because we have also marked this with tick A. We are explicitly annotating what Rust inferred in the previous lesson. I want to reiterate here that the connection is not really between the return value here and items. It's more between the return value and the referent from which items comes from. The original source of data that items is a reference to, we are saying that the return value and its lifetime is connected to that referent. We are using items as the source of inspiration to say whatever that original data source is and how long it lives, the return value, a reference, is connected to the same referent. Almost like copying the lifetime of items and where it's coming from to the lifetime of the return value. It's not quite a copy because the items parameter is actually going to go out of scope potentially earlier than the return value, right? So for example, in this example on line 11, the reference to cities exists as a single inline reference and it will cease to exist. But this reference of cities is going to populate for items, and we're going to use what cities knows, which is the lifetime of its referent of the city's vector. What this reference knows, we're going to take that information and say that the return value, the reference right here, must live within the lifetime of the original referent. And we are establishing that promise, that connection here. This does not affect anything in the body of the function. This is the promise that we are declaring, and the compiler and the borrow checker are going to make sure that we live up to that promise in here. Okay, so it's really about the mismatch between what we type here versus what we write in the body that the borrow checker is going to validate. So you might be curious, you might ask something like, isn't it completely obvious that the returned reference and its lifetime is directly connected to the referent of items? And the answer is yes, you could infer that logically. But remember, this is just the contract. It's sort of the exact same question as asking something like this. If I have a function called some function that accepts no parameter, and I declare a return type of I32, and I return a 5, it's like asking the question, why do we need to declare I32? Can't the compiler infer that it's an I-32 from the return value? And the answer is we declare the expectation, we declare the contract and the requirements here separate from the implementation so that the compiler can validate that 5 lives up to our promise here. Because maybe this function was meant to return a Boolean, and thus the compiler holds us responsible. So even if something looks obvious, like why doesn't the compiler just figure it out? The answer is because we're just declaring the promise or the obligation that the function will live up to, so that Rust can then parse the body and validate that everything is being upheld. It's the exact same principle with select first two elements. We're declaring the relationships here, so Rust can validate that what we do here, in this case, return a reference, is living up to this promise. So imagine that we defined this function before we wrote any of the code in main. If this function existed by itself, for example, in a library crate, Rust does not know all of the exact concrete lifetimes of the item's parameter and its referent. For example, if you wrote this code, somebody else could borrow your library crate and write code like this or code like this. These have completely different lifetimes. This is a concrete lifetime of cities, and this is a concrete lifetime of coffees, but they are different. They are different regions of code of different length. That is why the tick A here is called a generic lifetime. It's not a concrete lifetime, it's some hypothetical lifetime, and both this lifetime and this lifetime are able to play the role here, and the function's promise still holds true, which is that the returned reference must live within the lifetime of the referent of items. So in this case, the return value of 2 cities, which is this reference, must live within the lifetime of cities. And right here, the returned slice of 2 elements assigned to 2 coffees, Rust knows that it must live within the lifetime of its referent, which is coffees. Coffees is the original source of data. This reference right here is the thing that knows about the existence of coffees, and we've sort of transferred that knowledge over so that Rust knows that 2 coffees itself is now related to the lifetime of the coffees referent. 2 coffees is aware that coffees is the referent from which it is coming from and from which it was derived in the body of the function, and thus it knows that it is connected to it. So a generic lifetime is not an exact region of code. It's a hypothetical future region of code that can vary from execution to execution. All right. So once again, as we saw in the previous lesson, if we drop 2 cities right here, or rather cities, that is the referent, that is how Rust knows that 2 cities is invalid to use here, because it's made the mapping or connection between the lifetime of cities and the 2 cities reference that is dependent on it. All right. I want to repeat one more note, and that is from our lifetime annotation here, Rust knows that the lifetime of the return reference must live within the lifetime of the referent from which items is a reference for. It's not directly connected to the item's reference itself. It's connected to the referent from which items comes from. The source of data from which this reference arrives is a source of data that this reference's lifetime, the returned reference, the returned slice's lifetime, will be connected to and will live within. More on this in the next lesson.